Okay, this is going to make me feel better, and I'm going to actually show you how I solve that. Turns out, well, when you see one of these quadratics, you see if you can factor it into these two guys. Because if you get a product that equals 0, then it's really easy to solve. You don't have to pull out the quadratic formula, but you could pull out the quadratic formula if you really want to. All right, I'm going to unfoil this. 3c squared really pretty much only separates out into 3c and c. 1 really only separates out as factors of 1 times 1. So yeah, I've got 3c times c equals c squared. I got 1 times 1 equals 1. And I just got to check and make sure that I can get an outside and inside product to come up with this 4c. All right, so the outside product is 3c times 1, that's 3c. Inside product is 1 times c, that's 1c. And 3c plus 1c is 4c. Everybody's positive, it works just fine. You can FOIL that and recheck my work there, but I'm pretty sure it's right. So now I've got this product that equals 0. This should ring some bells. We haven't done this yet this year, but you've done it before. 3c plus 1 equals 0 now, or c plus 1 equals 0, because when I've got that product equals 0, the whole point of that was so I could do this. If I've got thing 1 times thing 2 equals 0, then that means either thing 1 must be 0 or thing 2 must be 0. So if I don't know which, either one could be 0, and that's what I do next. So solving each one of these separately, c could either be negative 1/3, that's a negative 1/3, or c could be negative 1. Okay, remember I started this all out by saying let's let c equals tangent of x. So really what I'm saying now is that tangent of x, because I didn't want to write tangent x. See, every time I wrote c here, I didn't want to write tangent x all those times. So I'll bring back the tangent x right now. It's negative 1, or it's negative 1/3. So back to this beginning thing, if I want to solve this equation for every possible value of x that could ever make this true, I've already got two values of even what the tangent could be. Tangent could be negative 1, or tangent could be negative 1/3. If tangent is negative 1, then it might look like this. It might look like it would be that. And this would be exactly, does it say radians? I'm supposed to do radians on this problem? I think I am supposed to do radians. Actually, in the book, they do this one, and it's in degrees. Lovely. So in degrees, and this is right after your chart, this is 135 degrees, that perfect 45-degree angle here. And of course, 45-degree angles there, or 45 here. These are all 45s. To make a slope of negative 1, this would be negative 45. Oh, let's do that positive. So let's make that, let's say, 315. Yeah, great. The negative 1's not so bad. The negative 1/3 is a little weird. Negative 1/3, if the tangent, no, that's the slope, is negative 1/3. So we're going downhill. We're going down, like down 1/3. So it's kind of like, it's sort of a shallow downhill thing, or something like that, where the tangent equals negative 1/3. How do I find that exactly? Well, I get my calculator out. Frankly, I don't want to have to figure that out. But the calculator is only going to give you one of these answers. It's only going to give you this one here. So I do that on the calculator. Where's my calculator? There it is. Let's go inverse tangent. Oh, am I in degrees? I'm supposed to be in degrees now, right? Calculator buttons are still kind of hard to push, but we get them. All right, degree mode. Inverse tangent of negative 1/3. And that gives me a degree measure of negative 18.43. Great. Yeah. In degrees, that would be this one down here. Negative 18.43 degrees. That is a possible, and that's approximate. I'll write here what I did. I did the inverse tangent of negative 1/3. And I got negative 18. So that one has that slope, but then there's an angle over here that's the same slope. In tangent, we're looking for lines that have the same. We're looking for angles that have the same slope. That produces a line with the same slope. I can just basically extend that line. Same thing I did here. This is the line that goes through the slope of negative 1. This is the line that goes through the 0, 0, slope of negative 1/3. It hits here at a rotation angle down that way of negative 18.43. It hits over here. Well, this little angle over here would also be 18.43. So I could think about this as 180 minus that. Or I could think about how, well, this is a whole straight line here. I could think about how there's really 180 degrees along this line. I could take this direction, which is negative 18.42, and add 180, which I guess would be just like taking 180 minus 18.43, and I will get what I want. 180. I've got this negative answer stored here, so I'll just add it. And I get 161.57. That looks about right. And if I didn't like this as negative 18.43, I could add 360 to that and find out what that is. But really, for the general solution, and I don't quite have enough room, I guess I will squeeze it down here. The final answer to this problem is it could be 315, it could be 135, it could be negative 18.43, or it could be 161.57, or any angle equivalent to that, which is add on 360 times n for all of it. So x is any one of these numbers. It could be, I'll make a set notation because there's just so darn many of them. 135 plus any number of rotations from that point, or, and this comma kind of means or, it could be 315 plus any number of rotations around the circle landing back on that point. Remember, n is any integer, so it includes forwards and backwards, because it could be positive or negative. So I might as well just say negative 18.43 here. I could say this. I could say the equivalent that's all the way around the circle that's a positive angle, 340 whatever, blah, blah, blah. But, if I don't, it's covered by this one, so this is just adding, if n is 1, that angle will be found, and it will be generated by that list that way. And the other one was 161. Or any equivalent angle that lands on that. So that's a whole bunch of angles. It's like 4 different infinite lists of possibilities for angles that may land on any one of those 4 things. Any one of those angles will solve this equation. So really that's about it. You have some sort of blast from the past review algebra kind of thing to do. At the end, you're going to end up with a cosine angle. You have to figure out what the angle is supposed to be, or a tangent, or a sine. If it's cosine, you need to find other angles that have the same cosine. Realize that you can always just change that angle to negative and it retains the same cosine. If it's tangent, you can add pi to it, which is the last problem we just did, or 180 if that's degrees, and you'll get another angle with the same tangent. And if it's sine, you subtract it from pi, or you subtract it from 180 degrees if you're talking about degrees, and you'll get another angle that has the same sine. This produces a reflected angle across the y-axis. This produces a reflected angle across the x-axis, and this produces the angle sort of at the other end of the same diameter as the original angle theta. So that's about it. Good luck, and I'll see you when I get back.